Today, we're diving deep into the world of Allen Bradley PLCs, or programmable logic controllers, and I'm thrilled to tell you that the knowledge you'll gain here will be a game changer in industrial automation. Whether you're completely new or want to sharpen your skills, this video is designed to help you level up and become more confident with PLC programming. In this video, we're taking a journey from the basics all the way to advanced techniques, exploring how PLCs have revolutionized the way industries operate. We'll be breaking down everything you need to know, from the foundational concepts to advanced programming and even troubleshooting strategies. Our goal is simple: to empower fresh engineers and control engineers across the globe. So, if you've got any questions, drop them in the comments, and I'll be happy to assist. Let's dive in and make industrial automation easier and more exciting for everyone. First, let's dive into one of the key elements of ladder logic, the output coil. The output coil is a crucial component in any PLC program. Think of it as the device that controls the action, whether it's turning on a motor, energizing a solenoid, or activating a light. In ladder logic, the output coil behaves like a switch that turns on when the input condition is true or high. It reacts to the inputs. So if the condition driving the coil is false or low, the output will remain off. Essentially, it serves as the bridge between your logical conditions and the physical actions in your system. Next, let's discuss the normally open NO contact. This symbol is incredibly common and represents a contact that starts open, meaning it doesn't allow current to flow unless the input condition is true. Once the condition becomes true, the contact closes and current is allowed to flow through. You can think of it like a gate that only opens when certain conditions are met. Perfect for controlling elements in your process that should only activate under specific circumstances. On the other hand, we have the normally closed NC contact. This works in the opposite way to the normally open contact. The normally closed contact begins in a closed state, allowing current to flow when the input condition is false. However, when the input condition becomes true, the contact opens and the current flow is interrupted. It's useful for scenarios where you want a device to remain active until a condition is met, at which point it turns off. These three elements, the output coil, the NO contact, and the NC contact, are the foundational building blocks of your PLC logic. Together, they allow you to create intricate control systems that can handle everything from simple on-off operations to complex sequences. Let's begin by understanding normally open, or no contact. Picture a light switch in your home. Most of the time, it's off by default, right? This is similar to a normally open contact. When the switch is off, no electricity flows because the circuit is open. In this state, nothing happens. No current passes through, no light turns on. Now let's shift to normally closed, or NC contact. This one works the opposite way. Imagine you're standing in front of a refrigerator. You know how the light stays off when the door is closed? That's because the circuit is closed, meaning no electricity is flowing to the light. But the moment you open the door, the circuit opens, allowing electricity to flow, and the light inside the fridge turns on. In PLCs, normally closed contacts behave in a similar way. By default, they let electricity pass through when they are inactive, but when they're activated, they stop the flow. So think of NC contacts as an automatic switch that works without you having to manually open or close it. It's like a safety mechanism, always allowing current to flow unless told otherwise. This is useful in systems where you want to ensure something remains on unless it's intentionally switched off, like emergency stop buttons or fail-safe conditions. Now, let's get started with the software for this practical training. I'll be using RSLogix 5000, along with the RSLogix Emulate for simulation, and the third application we'll be using is RSLinx Classic. We're diving into these tools because they are essential to get the software running and to enable downloading programs into the PLC. Let's begin with RSLogix 5000. I'll show you how to create a new project, select the appropriate controllers and modules, and configure everything you need. It's important to understand that selecting the right controllers and modules is crucial for ensuring your project runs smoothly. Here I am creating a new project. For this session, I'm selecting the simulator as my controller. There are multiple controller options available, but since I'm using the simulator, it allows us to test and troubleshoot the logic without needing physical hardware. In the simulator, I'll select that and name the project, for example, PLC programming. There's no protection required for this setup, so we'll move forward. Now that the project has been created, we can see the controller we selected displayed in the backplane. Next, I'll add some additional modules, like input and output modules. I'll choose digital I/O modules, but the selection depends on your specific requirements and the hardware you have available. In this case, I'll use this digital I/O modules to configure. Once selected, just click OK. These are all the options you can configure based on your needs, which will help you set up your project for success. Now I'll create another modules for digital output, but again, the selection depends on your specific requirements and the hardware you have available. In this case, I'll use this digital I/O module to configure the necessary inputs and outputs for the project. Once selected, just click OK. These are all the options you can configure based on your needs, which will help you set up your project for success. The controller has now been selected, and the input and output modules have been added. You can see in the controller properties what options are required beyond the default settings to customize the configuration to your needs. All of this is being done in RSLogix 5000, where we can fine-tune the system for optimal performance and functionality. Now, we're moving to the main routine where the actual programming happens. This is where we'll create the ladder logic that controls how the PLC interacts with the real world. The main routine is like the brain of your PLC program. It processes the input signals, executes the logic, and then sends commands to the output devices. In RSLogix 5000, we have several key programming objects to work with. First, there's the rung, which is the horizontal line where instructions are placed, similar to electrical wiring. Then we have contacts like normally open, NO, and normally closed, NC, which represent conditions that trigger actions. Coils represent outputs, like turning on a motor or light. There are also timers and counters for creating delays or counting events. These programming elements will allow you to build complex logic, automate tasks, and control machinery efficiently. Now let's start by adding a normally open NO contact and a coil to our ladder logic. The NO contact represents a condition that allows current to flow when it's energized or true. When the input condition is met, the contact will close and the logic will continue down the rung. Next, we need to assign an address to both the NO contact and the coil. The address for the NO contact links it to a specific input or tag in the PLC, like a button or sensor, allowing the PLC to monitor that input. Similarly, the coil must be addressed to the appropriate output, which could be linked to any device you want to control. Proper addressing ensures that the PLC knows which input to monitor and which output to activate. Now let's talk about controller tags. In RSLogix 5000, tags are used to identify and store data for inputs, outputs, and internal variables in your program. Controller tags are global, meaning they can be accessed from anywhere within the project. Each tag has a unique name and can be assigned to physical I/O points, memory locations, or program elements like timers and counters. By creating and managing these tags effectively, you ensure that your PLC program can monitor and control the necessary devices and signals. Let's assign addresses to our no contact and output coil. For the NO contact, I'm selecting the 0 bit of the input module. This means we're using the first input point for the contact. Once you've assigned these addresses, you can also add comments by using the Edit tag option, which helps label and organize your code for better understanding and troubleshooting later on. Similarly, for the output coil, I'll assign the 0 bit of the output module. This will activate the first output when the logic condition is met. With these addresses set, the PLC knows where to get the input and send the output. Once you've assigned these addresses, you can also add comments by using the Edit tag option, which helps label and organize your code for better understanding and troubleshooting later on. Now, verify and compile our program to check for errors. I'll click on the Verify button to identify any issues, and once resolved, we'll compile the program to ensure it's ready for downloading to the PLC. This step is crucial for confirming that our code is error-free. Now, I'm starting the RSLogix 5000 emulator and RSLinx Classic to set up for real-time simulation. The emulator allows us to test our PLC program without needing actual hardware, giving us the flexibility to see how our logic behaves in a controlled environment. It's taking a moment to open, so let's wait patiently. This process can take a little time, but once it's ready, we'll be able to continue with our training and see our program in action. And yes, it opened. I'm currently removing all the modules to set a new configuration. This will allow us to customize our setup according to our specific project requirements. It's important to start fresh to ensure everything is correctly configured for optimal performance. Let's proceed with this adjustment. I'm now adding the controller in the slots as defined in the project. This includes configuring the digital input, DI, and digital output, DO modules. Ensuring that these modules are correctly placed is crucial for proper communication and functionality in our PLC setup. Let's make sure everything is aligned correctly. RSLinx Classic serves as the communication link between our programming software and the emulator, enabling us to monitor inputs and outputs in real time. Let's get everything up and running so we can see our program in action. Let's make sure the RSLinx Classic drivers are properly configured, just as shown here. This step is essential for establishing a reliable connection between our programming software and the PLC. By verifying the driver settings, we can ensure that our system communicates effectively, allowing for smooth operation and monitoring of our project. After setting up the emulator 5000 and configuring RSLinx Classic, we are now ready to perform the download. This will transfer our program from RSLogix 5000 to the emulator, allowing us to run and test the logic in real time. Let's proceed with downloading the project and see it in action. I've now selected the controller, and we're ready to perform the download. This will transfer our configured program to the PLC or emulator, allowing us to test and monitor the system. Let's initiate the download and move forward with the simulation. Unfortunately, we've run into an error while trying to go online with the controller. This can be really frustrating, but it's a common issue. It often happens when the controller and I/O cards aren't placed correctly in their predefined slots on the backplane. Let's double-check the configuration to get things back on track. The error occurred because in the simulator, the controller is placed in slot 2, the digital input DI module in slot 3, and the digital output DO module in slot 4. However, in the program, the controller is configured in slot 0, the DI in slot 1, and the DO in slot 2. This mismatch between the actual slots and the program settings is the reason for the error. I'm now updating the Project I/O card settings to match the configuration in the simulator. This means setting the controller to slot 2, the digital input DI module to slot 3, and the digital output DO module to slot 4. Once the settings are aligned, we should be able to go online without errors. I'm saving the program again with the updated I/O card settings. I'll verify it to ensure there are no errors in the configuration. Once the verification is successful, we'll go ahead and perform the download to transfer the program to the controller for real-time simulation. Before proceeding with the download, make sure you've carefully read and understood all the instructions. Ensuring that everything is properly configured will help avoid errors during the download process. After a successful download, you'll be able to go online with the controller and monitor the real-time status. This will allow you to see how your program is functioning and interact with the system directly. I'm now enabling forcing to manually control and observe the input and output statuses. This feature allows us to simulate real-world conditions and verify that the logic is working as expected, even without physical inputs. As I force the normally open input, the output goes high, indicating that the condition is true. Conversely, when I disable the force on the input, the output will return to low, showing that the condition is now false. This demonstrates how the logic responds to input changes in real time. Now, I'm adding a normally closed NC contact using the same input address in another rung as the normally open NO contact. This setup will help illustrate the difference between the two types of contacts. While the NO contact allows current to flow when the input is true, the NC contact will block current flow under the same condition. Let's see how this affects the output during our testing. Both outputs are assigned different addresses to effectively test their behaviors. This setup will allow us to observe how each contact NO and NC affects its corresponding output under the same input condition. Let's see how these distinct addresses impact the output responses during our testing. After adding new rung, save the program once more and verify it for any errors. It's essential to ensure everything is correct before proceeding. Once verification is complete and no errors are found, we can download the updated program to the controller. After the download, I'm enabling the forcing again to perform a test. This will allow us to observe the differences in behavior between the normally open NO and normally closed NC outputs. By forcing the input, we can clearly see how each output responds and deepen our understanding of their functionality. We can see that the output with the normally open contact gets energized when the input is forced. In contrast, the output with the normally closed contact is de-energized under the same condition. This clearly demonstrates the fundamental difference between NO and NC contacts in our PLC programming. Similarly, we can add a timer to execute the output after a specified delay. This allows us to control when the output is activated based on the timing conditions we set. I'll simply add the timer here, and we'll dive deeper into how to use timers in our programming in the next video. I'll guide you through the process of tagging the TON timer in detail. We'll explore how to properly configure it and utilize it in our PLC programs, ensuring you have a solid understanding of its functionality and applications. Stay tuned. Welcome to the tutorial on timers in Allen Bradley PLCs. Today, we will explore three essential timers: the on-delay timer, the off-delay timer, and the retentive timer. Let's break each of these down step by step. First, let's talk about the T-on, or on-delay timer. The on-delay timer is used when you want to delay an output for a specific amount of time after an input condition becomes true. Imagine you have a light that you want to turn on, but you want it to delay for a few seconds before it does. This is where the T-on comes into play. When the input condition is true, the timer starts counting up to a preset time known as the pre- or preset time. The timer will accumulate the elapsed time in another variable called ACC, which stands for accumulated time. Once the accumulated time reaches the preset time, the output is activated. The key point here is that the timer only starts counting when the input condition becomes true. This timer is commonly used in applications like starting motors or delaying the activation of conveyor belts to ensure smooth operations. Now let's move on to the T-off, or off-delay timer. The off-delay timer operates in the opposite way of the on-delay timer. It delays the deactivation of an output after the input condition becomes false. Think of it like a light that stays on for a short period even after you turn off the switch. When the input goes false, the T-off begins counting for a preset time. Just like with the T-on, it uses a preset time, or pre, and accumulates time in the ACC variable. The output will remain active for the duration of the timer, allowing you to create processes where you want to maintain output even after the triggering condition has been removed. This is particularly useful in applications like fans that need to continue running after a machine is turned off to cool it down properly. Finally, we will discuss the RTO, or retentive timer. The retentive timer is a bit different from both the T-on and T-off. It is designed to remember the accumulated time even if the input condition goes false. This means that if you have a process that requires tracking time across different stages, the RTO is your best option. When the input condition is true, the RTO counts up to the preset time, just like the other timers. However, if the input goes false, the RTO retains the accumulated time instead of resetting it to 0. When the input becomes true again, the timer continues to count from where it left off. The output will activate once the accumulated time reaches the preset time. The RTO is useful in applications like batch processing, where you may need to track how long a process has been running, even if it stops momentarily. Now that we've covered the basic concepts of the T-on, T-off, and RTO timers, it's time to see them in action through practical programming. In this part of the tutorial, we'll dive into the software to implement these timers and help you gain hands-on experience with their real-world applications. I'll be picking up right where I left off in the last video, ensuring that you can follow along seamlessly. By the end of this session, you'll have a clear understanding of how to configure, program, and test these timers in Allen Bradley PLCs using the programming environment. We will start by setting up the T-on, on-delay timer, then move on to the T-off, off-delay timer, and finally, the RTO, retentive timer. I'll show you how to configure the timers, adjust preset times, and monitor accumulated values during runtime. So without further ado, let's get into the software and start programming these timers step by step to give you practical knowledge that you can apply in real-world scenarios. First of all, need tag for T-on timer. I'm going to create a new tag for the T-on timer within the controller tags. After selecting New Tag, it will prompt you to name the tag and select the right data type. For example, let's name it T1. Next, you need to select the correct data type for the tag. This step is very important because selecting the right data type ensures the proper function of your program. For instance, if you're working with digital inputs or outputs, you would select the Boolean data type, which is used for signals that are either on or off, like switches or push buttons. However, in this case, because we're using a timer, we need to select the timer data type. This ensures that the tag can handle the necessary functions specific to timing operations. Choosing the correct data type is critical for smooth programming, so always double-check that you've selected the right one for your application. In a similar way, I am now going to create another timer tag named T2 and assign it the proper data type. As before, I'll choose timer as the data type to ensure it functions correctly within the program. Choosing the right data type is crucial, as it provides the respective properties and tags that we can utilize in the program, as discussed earlier. You can see different options with timer data type, and each individual has its own purpose. After proper tag creation, we are moving to the main routine to program the TON on-delay timer, TUF off-delay timer, and RTO retentive timer. Sorry, I need some more internal tag to simplify the things for understanding. Let's name it Start Push Button and select the data type Boolean. I have to create another internal tag for Stop Push Button and need to give data type Boolean. After creating all the tags, I'm moving to the main routine to assign the time and observe the real-time simulation. To run the timer, I'm using the Start Push Button tag. This same tag will be used for all timers to start, allowing for a clear difference in operation. After that, I'm giving tag to T-on delay timer. I am assigning it to the T1 tag, and I'm giving 1 sec delay. 1 second is too short for a clear observation. I'm giving it 5 sec delay. In RSLogix, time is entered in milliseconds, so for 1 second we use 1000 milliseconds. Therefore, for 5 seconds, the delay value will be set to 5000 milliseconds, allowing enough time to see the timer in action. Now I will use the T1 bit to energize the coil. Once the timer reaches the preset delay, the T1 will turn on, allowing the coil to energize and complete the circuit. After that, I am assigning the physical address to output coil. Let's save the project and run a verification to ensure there are no errors in the program. Unfortunately, we found an error associated with the T1 tag. This is a good opportunity to understand the importance of using proper tag naming and assignments to avoid such issues. I'm selecting T1.dn because it will go high when the timer finishes counting, indicating that the preset time has elapsed. After saving and verifying this time, we didn't encounter any errors, which means everything is properly intact and ready to run. Okay. Now I'm starting the emulator and RSLinx Classic to begin downloading the program. This step will transfer the logic we've created into the simulation environment, allowing us to see how it runs in real time. After this, I'm moving towards downloading the program into the PLC. My controller is online, and I'm ready to proceed with the download. Before I start the download, it's essential to read and understand all the instructions carefully. This ensures that I follow the correct procedure and avoid any potential issues. I will check the communication settings to make sure everything is configured properly, including the correct driver and connection path. It's also important to ensure that the program has been verified and that there are no unresolved errors. After a successful download, I will move to the tags to change their state. For internal signals, I only have toggle bits available, as these are not physical I/O signals. Therefore, the force on and force off options are disabled for these internal tags. After toggling the Start Push button, the on-delay timer begins its countdown. Once it completes the set delay, it will energize the output, activating the corresponding device or action in the system. I'll try toggling the Start Push button again to observe the behavior of the on-delay timer. This will help you to understand how the timer responds each time it's activated and ensure it's functioning as intended. We have seen that when the input becomes false, the timer's accumulated value resets to 0. This indicates that the timer has stopped counting, reflecting the current state of the input signal. Let's move on to create the logic for the off-delay timer and see how it works. To start the timer, I am using same start push button tag that previously I used. This timer will start counting down once the input signal turns off, allowing us to understand its behavior in this scenario. I'm assigning the off-delay timer to the tag T2 that I have already created and setting the same delay of 5 seconds, just like I did for the on-delay timer. This will allow us to observe the functionality of both the on and off delay timers. Next, let's connect the normally open contact associated with the T2 tag to the coil. This will allow us to observe the coil's behavior during energization and de-energization, providing clear insight into how the off-delay timer affects the output. This time, I will carefully select T2.dn to avoid any mistakes. Ensuring the correct tag is chosen is crucial for accurate functionality in the logic. Now I will assign the coil for the output, just as I did previously. This will allow the output to be energized based on the state of the T2 off-delay timer. Now, you can see both timer states displayed on the screen, along with their respective outputs. Both timers are set to the same time delay of 5 seconds. Let's save the logic and verify for any errors. If the error count is 0, we can proceed with the download. This step is essential to ensure that the program is free of mistakes before transferring it to the PLC. Select the controller and perform downloading after carefully reading the instructions. After the successful download, we're now at a pivotal moment to understand the key differences between the T-on and T-off timers. Observing how each timer behaves in response to input signals will provide valuable insights into their functionality and application in control systems. Let's toggle the Start Push button and observe the timer responses. You can see that the on-delay timer has started counting seconds, but the off-delay timer has not started yet. This behavior is expected as the off-delay timer only activates when the input signal is turned off. As I toggle the off-delay timer started, I can repeat the step for your understanding. As we do this, pay close attention to how each timer reacts. The T-on timer will begin counting every time we toggle the Start button on, while the T-off timer will only activate once the input is turned off. This back and forth will help us understand their distinct behaviors and how they play critical roles in our control logic. This clearly indicates that the on-delay timer energizes the coil after 5 seconds, while the off-delay timer de-energizes the coil after 5 seconds. This behavior highlights the fundamental differences between the two timers and their respective roles in the control logic. Let's move on to the retentive on-delay timer, or RTO, to explore its behavior and create the necessary logic. I am using Start Push button as previously used, and now selecting the RTO to place it. I need to create a new tag for the retentive on-delay timer, as we haven't done this yet. We will follow the same procedure as before to ensure consistency in our setup. We'll start by adding the tag for the retentive on delay timer first. Following that, we'll set the timer for a 5-second delay, maintaining consistency with the delay times we've used for all the other timers. Again, use a normally open contact associated with our RTO timer, labeled T3, to observe how it activates the coil. By integrating the NO contact with the RTO timer into our logic, we can visually confirm the operation of the retentive on delay timer. When the input signal is activated, the coil will energize after the 5-second delay, and it will retain that state even if the input signal goes low. After saving and verifying the logic, we'll move on to download the program and test all 3 timers: the on delay, off delay, and retentive on delay timers. Finally, we've reached the stage where we can observe all 3 timers, on delay, off delay, and retentive on delay, working together in our program. This is a crucial step in understanding the distinct behaviors of each timer and how they operate in real-time control logic. By running all 3 timers simultaneously, we can see their unique characteristics side by side, giving us a comprehensive view of how each one functions under different conditions. This practical comparison will help you better understand their applications in real-world scenarios, ensuring that we know which timer to use for specific control processes. Let's take some time now to observe their behavior and gain insights into their individual and combined operations. When I toggled the Start Push button, both the on-delay timer and the retentive on-delay timer immediately started counting. The on-delay timer will energize its output once the 5-second delay has passed, while the retentive on-delay timer begins its count as well, but with the unique ability to retain its accumulated time even if the input is deactivated. This allows us to see both timers in action, side by side, and compare how they handle the input signal and time delays. You may have noticed that while toggling the Start Push button, the retentive on delay RTO timer didn't reset. Unlike the standard on delay timer, which resets to 0 when the input signal is interrupted, the RTO timer retains its accumulated value. This unique feature allows the RTO to resume counting from where it left off when the input is reactivated, instead of starting over. This is particularly useful in scenarios where maintaining the accumulated time is important, even if the input signal changes. Now I'm creating the logic to reset the retentive on delay RTO timer using Stop Push button. Since the RTO timer retains its accumulated value even after the input signal is toggled off, we need a specific reset mechanism to clear the accumulated time and restart the timer from 0. Here I am give T3 tag for reset. Now I'll proceed with downloading the updated program to the PLC. We'll follow the same steps as before, saving the logic, verifying for errors, and downloading the program into the controller. Once the download is complete, we'll test the reset functionality by toggling the Start Push button, allowing the RTO to accumulate time, and then triggering the reset to observe how the timer responds. This will ensure that the reset logic is working correctly and the timer is cleared as expected. After toggling the Start Push button, all timers started operating according to their respective functionalities. The on-delay timer began counting, energizing the output after the set 5-second delay. The off-delay timer activated, keeping the output energized for 5 seconds before de-energizing it. Meanwhile, the retentive on-delay timer also started counting, but unlike the others, it retained its accumulated time. Now I will reset to reset the RTO time. When the reset coil is energized using Start Push button, it resets the accumulated time of the retentive timer on, also known as the RTO timer. The RTO timer keeps track of elapsed time even when the input condition is false, but energizing the reset coil clears the accumulated time and starts the timer fresh the next time the input is true. I hope you're finding this video helpful. If you're passionate about learning new skills and want to keep improving, don't forget to subscribe to stay updated with more tutorials and tips. Your feedback matters, so feel free to drop a comment if you need any help or have questions. I'll be here to guide you through your learning journey.